Okay, so what I want to do now is, let me see, we are ahead of schedule. I want to go to Mr. Phil Bouchard. Who looks like he's in here twice. There we go.
Okay, so I start right now.
Yes, sir. Would you like to present now?
Sure.
Okay, and if you'd like, let me do a brief introduction just for anyone who doesn't know. So Mr. Philippe Bouchard is going to provide a visual update on the finite theory gravitomagnetism merger that can explain the universe at all scales and beyond. So his goal is to perfect reverse engineering of galactic rotation curves, a clear explanation for the inflation of the universe, but without the need for dark matter or dark energy. And he's hoping to even reverse engineer the distance from the universal core of our universe in a robust way. So all of these things within this model that he's been working on, they don't violate the laws of conservation of energy. And he is also hoping that the work he's doing can help to provide some clear explanations for UAP secondary effects, such as possibly force fields, time rate fluctuations, and maybe even gravitational effects. So Mr. Bouchard, thank you so much for joining us, sir. Let me hand things over to you, and I will mute myself and everybody else out.
All right, thanks, Tim. I'm gonna share my own app. All right. All right, good afternoon, everybody. This is a presentation of finite theory and gravitomagnetism that replaces general relativity at all scales, from the solar system scales to the visible universe to the greater invisible universe. Sorry about that, my app froze. Okay, there it is. Okay. Okay, so here we see that the traditional light bending experiment that was done earlier in 1919, this century, where we see that general relativity light bending prediction is twice as much as the Newtonian light bending. But I have to say that general relativity was already adjusted by the perihelion precession in the first place, so it's not really a prediction. So there's room for discussion over there already. The gravitational redshift we see here, a laser bouncing back and forth on the mirrors, starting in red is going to blue shift, where the elevator goes down in altitude. So basically, general relativity's redshift refutes special relativity's locality postulate. Regarding the black holes, we see that black holes are either singularity or wormholes with general relativity. So if there's a black hole collision, then we'll end up with another singularity quite simply. So that's the prediction that general relativity will come up with. So here we see slowly that two singularities are about to collide with each other, which will create another giant singularity. Sorry, my mic is a little bit slow. It's a lot faster in Linux. So there we'll end up with a greater singularity, quite simply. So that's what general relativity will predict. Regarding the inflation of the universe, general relativity predicts that the universe inflates like a bread in an oven, but it also loses energy, so we don't really know what happens with this to this energy there. It breaks the laws of the conservation of energy, right? So you know that general relativity fails at this scale already. So we see here the inflation of the universe, and it loses the energy redshift. So there's no clear explanation for that. The energy just converts into dark energy or something like that. So nothing, it's not very clear. The explanation is not very clear what happens to this energy. And now, so here with finite theory, and here's finite theory and gravitomagnetism. I have to start with the measurement units of gravitomagnetism because they're much simpler than what is written in the textbooks. If you simplify the measurement units, you end up with some similarities with electric and gravitoelectric field, which is the standard gravity, the magnetic and gravitomagnetic field, where you just add a factor here, which is the ratio of the kilogram and the coulomb that you need to multiply or divide with to convert one with the other. So I'm talking about this factor here. This little factor will do the proper conversion with the electric, gravitoelectric, and the magnetic and the gravitomagnetic field. But basically it's the same measurement units, but there's no big difference there. We also see below the magneto-hydrodynamics vortex apparatus in development to generate gravitomagnetic field, which will induce a simple gravity vector at the same time. So regarding the galactic rotation curves, here is the extremely simple and clean equation I use to represent them. It consists of the main orbital velocity factored by the time dilation and slightly altered by its own spin as well. Because remember that with finite theory, objects do have their own superposed co-moving gravitational framework, which will emerge with massive objects such as galactic bulge. Sorry. So about the ready range and mass of the visible universe, if we take the inside the sphere gravitational potential distribution formula of the entire visible universe, the mass density of the visible universe and the volume of a sphere will end up with the following possible ready range and mass ranges, or 2 times 10 to the 23rd meters and 2 times 10 to the 43 kilogram respectively. That's 2,000 times lesser than the radius estimated by mainstream science regarding the ready, and 100 million times lesser than the mass estimated by mainstream science. So here's the mass here that we can deduce. It's really a range, and that range is determined by if you do a graph of the possible, here, little r is the position of the Milky Way in the visible universe, and the capital R is the radius of the visible universe. If you do a graph of those, you'll see that there's a maximum range that you can have. So it's the little r won't go over the greater R. So everything is explained in my manuscript here, fornax.com, files, PDF, finite_theory.pdf. So I explain all these equations in my manuscript. And with that information and some mathematics of the Hubble's constant, we can solve the maximum velocity of the visible universe, which would be around 637,000 times 1,000 meters per second. So all these equations again are explained in my manuscript. All right. Regarding the energy density and the acceleration of the visible universe, I use the energy density here of a photon, where we see the electric field and the gravitomagnetic field here equals to the Planck constant times frequency times n, where n compensates to the density of the energy, where the density of the energy really is the frequency of the gravitomagnetic field divided by the gravity permeability and the Planck constant. The electric field and the magnetic field can also be decomposed into the Kc constant, which is the square root of the electromagnetic permeability divided by the gravity permeability that we see on the right right here, on the top right. And this is what I call the Kc constant. And when we decompose the equation here, there's also another important property where the electric energy density equals the magnetic energy density. So one equals to the other, so we can simply use the middle formula then at the bottom here. So where the electric field is equal to the magnetic fields times the speed of light of the gravito-electric field equals the gravitomagnetic field times the speed of light. So can I scroll down? Yeah, okay, one. Yeah, so it turns out the acceleration of the visible universe is 6.7 times 10 to the minus 10 meters per second square. There are some equations we can see, unfortunately. Oh, yeah, right here. Sorry about that. Yeah, right here. 6.7 times 10 to the minus 10 meters per second square. Furthermore, just with the simple equation, we can deduce a lot of properties of the speed of light here. We see at the bottom of the for the gravitational redshift on the left. So this is the, it's kind of based on, it's similar to the variable speed of light of that Einstein came up with in his first manuscript, but later kind of diverged into his tensor calculus formula, but it was later extended by Mark, Decay, and all these people. and I'm kind of extending it on my own. I did all that work without knowing about these people. It's just purely based on the on some book that I'm referring to in my manuscript. So what is left to deduce is the position of the universal core, or the enormous mass that creates the gravitational potential differential the visible universe is traveling through. So if we take the simplified Newtonian acceleration equation, where we strip out the mass of the visible universe, we'll end up with the acceleration of the universe equals Newtonian's gravitational constant times the mass of the core divided by the position of the core square. Also, by definition in finite theory, Newtonian G also equals to G. The G also equals to the speed of light squared divided by the fudge factor of the invisible universe. So basically, the Newtonian, since h is not a constant, it's a variable. That means the Newtonian constant fluctuates. It's not a constant at all. It just depends on the scale you're using it. You're at. So if you're at the Milky Way scale, it's going to equal something. If you had the supercluster scale, it's going to be different. So everybody wonders if that's a constant or not, but it turns out G is not a constant. And also the fudge factor of the even invisible universe at that scale is simply the fudge factor equals the mass of the universal core divided by the position of the universal core, the distance you're away. So it's simply the gravitational potential without the G constant. It's that simple. It's very similar to the Dickey's formula there. Also, you might want to take a look at his work. So we already know that the acceleration of the visible universe, since we already know that the acceleration of the visible universe, we can also solve the position of the universal core, or 1.3 times 10 to the 26 meters, as we see at the bottom right. The order of magnitude of the latter is exactly the same as the order of magnitude of the radius of the visible universe, as deduced by mainstream science. So there's a huge similarity there. Regarding the Earth's tides here, I'm showing using a software and multiple microgal measurements. Sorry about that. And multiple microgal measurements that around the planet, that there is a difference with the prediction of the measurement. So that means a gravimeter at 6 p.m. in the afternoon will not measure the same thing as a gravimeter at 6 a.m. in the morning. Because the gravimeter is either perpendicular or aligned with the sun, and the prediction and the residual actually is very proportional to the derivative of the gravity prediction. So that means the residual is very consistent with the fact that the gravimeter is either perpendicular or aligned with the sun, which means there is obviously ether or a superposed co-moving gravitational framework. So that's evidence right there that there's either ether Lastly, an important side note in my paper, I refer to another paper showing the flyby anomaly is also proportional to the alignment of the Earth relative to the Sun. The light bending here compared with Newton is exactly the same as predicted by general relativity, or twice what Newton predicted for the angle of the light bending. So all these solar scale predictions are exactly the same as what general relativity predicts, but I'm using the variable speed of light. It's the same thing with the perihelion precession disparity. Everything is shown in my paper. So you basically have the Newtonian acceleration that modifies the light bending and the perihelion precession, but you also have time dilation that you add on top of that. That's why it doubles the factor as the one predicted by Newton. It's very simple. Regarding the black holes with finite theory, black holes have a maximum mass density, so there's no singularity. And when two black holes collide, then you'll create a bigger aggregate black hole, but it's not going to be another singularity. That was proven in 2021 that two black holes colliding will gain in mass and size. So this is exactly what matches the observation and what Stephen Hawking was predicting as well. So this is another disproof of general relativity that mainstream scientists silently dismisses. So we slowly here see that the collision of two black holes as predicted by finite theory will just create a bigger aggregate black hole. So there's no singularity in question here at all. There's no wormhole in all that. By the way, a wormhole is connected to a white hole, but what defines the position of a white hole, there's no definition. General relativity does not come up with any definition on what predicts the coordinates of a white hole. So that's another fuzzy thing of general relativity. Regarding with the galactic rotation curve equation I've shown earlier, finite theory is able to reverse engineer the rotation curve of pretty much all galaxies. By reverse engineering the rotation curve, I'm able to figure out the maximum fudge factor the galaxy is, and it's around 1 times 10 to the 28 kilograms per meter. So that's how I'm able to say that the maximum mass of the universe can be, and with the maximum radius of the universe can also be. Because the fudge factor of the Milky Way cannot be greater than the fudge factor of the cluster, which in turn cannot be greater than the fudge factor of the supercluster, which in turn cannot be greater than the fudge factor of the visible universe, and so on. The rotation curve are very consistent, so there's no big mystery here also. The superposed co-moving gravitational framework actually says that you have the stars spinning around the core and the galaxy of the core of the galaxy, but the bulge itself is also spinning because of its mass. So again, what we've been deducing as dark matter for so long is just a matter of adding a spin to the galaxy, and it solved the problem. So here we see the various rotation curves of. I have a software that did that very quickly in C++ for 500 galaxies. It's on my account GitHub. You can download it and compile it and check it out yourself. So yeah, it's very simple. All co-moving framework are kind of relative. There's no absolute grid. That's a postulate of finite theory and a mistake of general relativity to assume there's an absolute grid, like a hard-coded Cartesian grid or whatever, and that everything is relative to that grid. So with finite theory, even the rotation of the masses are relative. So that's the main difference between finite theory and relativity. The expansion of the universe here, we see that using Newton or the dark red is faster at the beginning, but it's actually slowing down. By using finite theory, the time contraction actually speeds up the expansion of the galaxies, so it ends up that the race is being won by finite theory here, who reaches a greater distance faster because of the time contraction. Again, the galaxies are expanding faster and faster because of the time contraction. So that removes the need for dark energy right there. So the expansion really is because of the time contraction, not dark energy. Last but not least, the inflation of the universe here is similar to general relativity, except that the universe itself is traveling through a gravitational potential differential as previously stated. So that makes the universe expand because of the time contraction. But you also need to add the gravitational redshift that we thought that the inflation of the universe was causing the loss of the energy. Really is that because of the fact that the visible universe is redshifting its electromagnetic energy and converting it into a balanced gravito-electromagnetic energy. So it's very simple. The universe has a speed which would make sense, and the gravitational redshift makes it apparently losing electromagnetic energy. So regarding regarding the gravitomagnetic field, here's a real abduction of Travis Walton as shown in the movie Fire in the Sky. So it's really a gravitomagnetic beam that induces a gravitoelectric beam that propels Travis Walton up from the ground, and also from that abduction scene. It was said that the trees surrounding the abduction area grew faster than what was at the other places. So it's really contraction of time that put the trees on fast forwards and speeds up their growth. So it's really by playing with gravity that you can play with the time rates, and you can also easily accelerate the growth of the trees and vice versa. Also, by using the gravitomagnetic field, you can create a force field by stopping anything from reaching you. You can dilate time by dilating time. You can stop anything, including lasers, nuclear bombs, missiles, pretty much everything from colliding at you, because you just locally block the time. there's a video of UAPs where I think the military is trying to attack UAPs, and the missiles are completely ineffective. They just blow up on their own, and they don't affect the UAPs at all. I did try to find that video, but apparently it got erased from YouTube. But it's pretty much the same thing here. You block the time. If you block the time, you modify the speed, the acceleration, the molecular cohesion. You affect all these. So, and nothing can really touch you. You can also create tractor beams and freeze entire vehicles from traveling, and put them on hold and freeze everything within that vehicle. That's you need a pretty strong beam, but in theory is possible to do that. Also, you can create what I call blink drives. By contracting time, you can speed up time within an artificial tunnel. And you can travel faster than the speed of light very easily. But please note that the gravitomagnetic field loses energy relative to the distance. Therefore, to create such an astronomical artificial tunnel, you would need new technologies such as gazers, in which, similarly to lasers, wouldn't lose energy relative to the distance. So it's, again, in theory, it's highly possible, but I've been looking around for gazers. They still have theoretical ways of doing that, but there's no way I'm aware of, or that the general public is aware of to build those gazers. But I think we would need to study quantum physics a little bit better. Talking about quantum physics, the standard model is pretty is not gonna last for a very long time, because it has problem with the muons, some pink quark, I think, that was discovered in the protons and neutrons. So the standard model is not going to last very long. So we'll need a new alternative pretty soon to to study further. We'll need to rewrite that from scratch, basically, because it just doesn't work as it is right now. So thanks for your time. I really appreciate. And if you have questions, please go ahead. Thank you.
Awesome. Phil, thank you so much. Let me see. I'm going to allow people to unmute themselves. And again, that is Option Y on Mac or Alt Y on Windows to ask questions. So that was a very in-depth drill down. And I know that you published a lot about finite theory online. Do you have a link that you could share where people could learn more about that? They're probably gonna have to review that.
Yeah, there's a manuscript with all the updated equations. It's fornox.com/files/pdf/finite_theory.pdf. Again, it's fornox.com/files with an S/pdf/finite_theory.pdf.
Okay, and maybe you could put that in the chat if that.
So fornox. Pause. I know it by heart. It's pretty easy to remember. Finite.
Okay, so yeah, in the meantime, if anybody has questions, Harold, go for it, sir.
Yes, you brought an interesting point. You mentioned about the the gravitomagnetic beam. Do you have any links or any information about who is doing that kind of work about the gravitomagnetic beam? Where can we find more information? Thank you. Great presentation.
Yeah, thanks. Well, there's Tajmar. Tajmar, we all know about him. He did some work. It got kind of silently dissolved. I don't know where he's at right now, but he was on his way to do that. There's also the PDF. The PDF I posted in the APEC WhatsApp group. It's a book that is free. There's a lot of great information in there if people read it. I also forgot to mention, there's obviously a discrepancy on the amplitude of the gravity permeability. So what the book says, what the gravity permeability is by far off what is found by experimentation, because the textbooks are based on the analogy, and it's not a derivation or anything like that. So it's way off the chart. It's completely wrong, and I have made a lot of evidence that shows that a lot of experiment shows that the gravity permeability is off by a large factor.
Okay. Thank you.
Awesome, Harold, thank you so much. Okay, so I'm going to put your hand down. Mark, go for it, sir.
Hi, I would like to know more about the Kc constant that you mentioned in your mathematics. What is the meaning and interpretation of that?
Yeah, so that's some sort of constant that you can use to convert the electromagnetic and the gravito-electromagnetic energy densities. So it's just a factor that you add and you convert one with the other. I did.
Does it have a physical meaning?
No, well, it's a conversion factor with the Coulomb and the mass, the real mass and the charge, what is emitted by a charge. I did try to I did go at the quantum level. I did try to abstract the mass and the energy, but apparently the mass is very different than the energy. But there's no, it's kind of a equivalence there. Just a constant that makes the equivalence with the mass and the charge. So I did try to find its true meaning, but at the quantum level, but I was not able to develop further on this.
Okay. Have you ever attempted to calculate the density of space?
Well, the density of space is pretty much the density, because Einstein uses a curved space-time and all that. I mean, with finite theory, I use a standard Cartesian grid. So the gravitational potential is pretty much the density of space, where if you cross the event horizon of a black hole, that's the maximum density that you can have. So if if you fall into a black hole, it's perfectly safe because you'll just stop at the event horizon. You'll never cross the border. At the same time, you'll travel into the future. So what Stephen Hawking was referring to as spaghettification will never happen because you'll never cross the event horizon. In contrast, you'll just time travel into the future until the black hole evaporates, and in theory, it's perfectly safe to jump into a black hole.
Thank you.
All right.
Okay, so Mark, thank you, sir. And let me go to Jim. Jim, go for it, sir.
All right, I enjoyed that analogy. Perfectly safe to jump into a black hole. I think I have several times. But anyway, I do find it fascinating that what's your theory, the finite theory, because it's actually anti to everything we've done. But I wanted to question about it. What's your thoughts on what the James Webb Telescope is revealing now? But some of it jives with what the empirical observations we're seeing. We're actually peering back, and it seems to be moving farther back. I don't know if you agree with that. I think that's pretty.
Yeah,
cool.
the expansion of the universe as predicted by general relativity is far off by what the cosmological microwave background is predicting. So there are huge discrepancies. The galaxies far away are far more developed than what general relativity predicts. Everything is pretty far off than what general relativity predicts. I saw the James Webb's, I'm following the James Webb's observation, the recent one, and that's what they were saying. So yeah, I didn't do a lot of. I could do some calculation on the cosmological microwave background. It seems to be an interesting subject, but I didn't go as far as that yet.
I don't think the public has gotten any of that data yet, so it's going to be interesting as we see that, and what you're comparing with dark energy and other things. So it's exciting stuff. Thank you for your presentation, by the way.
Yeah, you're welcome. I also forgot to say just a little parenthesis here on the. I know a lot of people ask about high energy physics, and I don't mention it because it's very simple. But if you have, so finite theory disregards length contraction and mass increase. Length contraction, by the way, was never directly observed. So, and mass increase kind of compensates for the momentum of the accelerated particle. But actually, if you dilate time, if you do time dilation, you don't need mass increase to change the momentum, because the dilate time is going to affect the momentum because of the time factor within the equation itself. So you don't need mass increase at all to change the momentum of an accelerated particle. So just a little parenthesis here I forgot to mention, but apparently it's people complain that I don't talk about that. Yeah.
Awesome. Okay. Well, thank you. So let me go to Mr. Michael Boyd, who's been patiently waiting. Sir?
Hello. That was great, Phil. And obviously you have a coding talent too. My question is sort of follows the previous one. I put in the chat here a little comment and a link to a YouTube video where basically it's about the Webb telescope, and basically what I'm saying in the chat is that what it shows is space itself is expanding, not the matter within it. So essentially what they did is they went back to roughly 100 million years after the so-called Big Bang, and they looked at galaxies like ours, and they were the same size. So like, for example, what my hypothesis is that there's a manifold of events in space-time that's independent from the matter within it. So space-time is a substance. It moves independent from what's in it, the stuff.
Yeah.
And in that case, you have a forever universe. There is no bang. So I'm curious. And then after I put that, Todd put a comment. He said, space isn't expanding, matter within it is contracting at 6.8 nanometers per meter per century, i.e. the Hubble constant, which is, I think that's a cool comment.
Thank you.
And so I'm just curious your thoughts about that. Do you think the universe is contracting, or do you think it's expanding? And do you think the matter is changing within it?
Yeah, thanks for the question, because it brings another point that I mentioned, I think, in the APEC WhatsApp group very quickly. By the way, another parenthesis here I forgot to mention. Einstein says that the universe inflates and expands and all that, and that's what explains the expansion of the universe. But if space expands and the position of the galaxies is modified, then why the volume of the galaxies is not expanding as well? So that, for me, that makes no sense. The volume should expand as well. Just by the way, so that's another thing I forgot to mention. There's so many things that I don't even know where to start. But yeah, so that's when you talk about the expansion of the universe, for me, it's there's not much to say other than, for me, it doesn't work because of all these things that don't stick together. But I say it expands. I say the universe expands because of the time contraction and the momentum that we're traveling away from the universal core and all that. So it moves, it either contracts or expands, but right now it expands, but it can contract later on.
So would you suggest it's in a jet, for example?
A jet,
like a black hole has a jet at the two poles?
Oh yeah. Yeah, it's for the jet streams of the black hole. I think I'll leave that to the black hole itself. I'm not gonna add the jet streams to the universe itself. It's possible, but you know, I don't like to conclude on things that are not clear to me. And you know, beyond, like, for me also, one thing I want to say is a lot of scientists try to explain what happened before the universe, and if there are multiple, and Stephen Hawking himself was trying to explain if there are multiple parallel universes and all that, but they can't even explain the flyby anomaly. So I think they should start by explaining the flyby anomaly correctly, and then they can expand at greater scales. So it's the same thing with me. I can explain up to the universal core. I assume we're traveling away from a universal core. It makes a lot of sense. Everything sticks together. Because of the time contraction, there's some you know, the universe expands and there's gravitational redshift and all that. But I don't like to talk about things that are not very clear to me. And for me, my explanation all sticks together, is very robust. It's all based on the mass density of the universe. And from there, I use, you know, high school algebraic equations. They were not easy to figure out, but it turns out they're easy to explain. And so, yeah, that's, I wouldn't want to venture on things I'm not aware of.
Okay, well, that's fair. Thank you for your answer, and I appreciate your curiosity. I share it.
Yeah.
You're welcome. And please take a look at the manuscript. Everything is very clear and neat and very easy. It's high school algebra, and yeah, I'm pretty. Hopefully, we can put an end on all these mysteries.
Okay, well, Phil, thank you, sir. So let me do this then. We're a little bit ahead of schedule, but I think we're out of questions. So what I want to do is ask everyone to give Mr. Philippe Bouchard an enormous hand. Phil, thank you, sir. Thank you so much. Thank you so much. I know it's very intense. That was very intense, and it's not easy to deliver that. So thank you for going through all of that. You know, it's especially when you're in a public venue and you have a lot of people, there's always the stress involved with that. So thank you so much for
Yeah, you're welcome. And it's hard to explain, and that's why I decided to make it more visual.
Yeah, and it helps. It helps.
The hassle of that, just to do this great presentation. And thank you to the team, and thanks Jeremiah for his effort, and Gerald and all that. Hopefully, I'm not sure what's behind they can't present, but if they got a good reason, unfortunately, I understand them in advance if they can't present. But so yeah, thanks the team again.